Let us solve a problem on diffraction grating. We have got a monochromatic light from a helium neon laser which has a wavelength of 632.8 nanometer. It's incident normally on a diffraction grating containing 6000 grooves per centimeter. So that's the value of n. We will be writing it as 6000 lines per centimeter. Grooves means the lines on the diffraction grating. Now we can see that it is in centimeter per centimeter, so we need to convert that into meter. 1 centimeter is 10 to the power negative 2 meter, and which gives us 600,000 lines per meter. Now this is the value of n for all the parts which we see from A to F. Okay, the first part is asking you find the slit spacing for the grating. So it's asking you the value of D. The second part is asking for the angle, which is theta, for the second order maxima, which is observed. So the value for second order maximum is m is equal to 2. Now we will first solve part A. It's asking for D. N is given as 600,000 lines per meter. We have the value or the formula for D, which is 1 over n. We can substitute the value of n, use our calculator, and get the answer as 1.67 into 10 to the power negative 6 meter. So that's our slit spacing. And it will remain the same for all the parts which we are going to solve. Now in part B, it was asking for theta and it was giving you m as 2. So now we will use the second formula for diffraction grating, which is d sine theta equal to m lambda. We rearrange sine theta because we want the value of theta, and then lambda is given in the problem as 632.8 nanometer. We use that and we use the value of D as 1.67 into 10 to the power negative 6, and we get sine theta as 0.758. To get the value of theta, we have to do sine inverse of 0.758, and we get the value of theta as 49.3 degrees. Part C is asking you, is third order maximum possible? Is it possible to get a third order maximum for this particular diffraction grating and for this particular wavelength of light? So we are going to use the formula for diffraction grating, which is d sine theta equal to m lambda, and we will rearrange it for sine theta. And we are going to substitute the value of m as 3, lambda and d we know from before, and we get sine theta as 1.14. Just a quick advice here, when you use the calculator, the denominator number, put it in brackets so that we don't make a mistake in the calculation. So we get sine theta as 1.14. Now we know that the maximum value of sine theta which is possible is 1. This means that n equal to 3 is not possible because we are going to get here sine theta greater than 1. The value of sine theta here is 1.14, which is greater than 1 and which is not possible. Sine theta cannot be greater than 1. This means that n equal to 3 is not possible. Next question, part D, it was asking how many bright fringes are formed. That means how many total bright fringes we can get with this particular diffraction grating and with this particular wavelength of light. So because n equal to 3 is not possible, so that means the maximum number of or the order which we can get is 2. So plus minus 2. So the total bright fringes which would be formed is 2 above and 2 below and 1 in the center. So 2 up, 2 down and 1 in the center, and we get that as 5. So the total bright fringes which can be formed is equal to 5. Next, what is the highest order possible if lambda is 500 nanometer? Now we can see that now the wavelength has changed. So the question is asking you, what is the highest order possible? When lambda was 632.8 or 632.8, we got the maximum order as n equal to 2. Now we have changed lambda and we want to find out what will be the highest order possible. So again we are going to use d sine theta equal to m lambda. We rearrange it and we know that because it's asking for highest order, that means sine theta, the maximum value of sine theta is 1, and we are going to put sine theta as 1, rearrange the equation for m because we want to find the order. D is 1.67 into 10 to the power negative 6 because it's the same diffraction grating, so the number of lines remain the same, and therefore the slit spacing will also remain the same. But lambda has changed, which is 500 into 10 to the power negative 9, and we use our calculator. Again, the denominator, enclose it in bracket. When using the calculator, we get the value for m as 3.34. So the integer which is there is 3, so the highest order which is possible is 3. The last question, does a diffraction grating with more lines have a smaller or larger separation between adjacent principal maxima? So we again write the formula for diffraction grating, which is d sine theta equal to m lambda. It's asking for the separation between adjacent principal maxima. That means it's asking for sine theta. We know that d is equal to 1 over n. So we are going to use these formulas together. Let's see how to do that. So sine theta is equal to m lambda over d. So sine theta, that is a separation between adjacent principal maxima, depends on d, and d depends on n. So the question is telling you n is made more, we are having more lines, that means d will be less, and if d is less, that means sine theta will be more, which means that there will be larger separation between the adjacent principal maxima.